Okay, so at the end of the last lecture, we were partway through the proof of cell decomposition. So what had we done? We'd shown if we have 1 up to 1n minus n, or up to 1n, and 1 up to 2n minus 1, we get 2n. And now we have to do the other one. We have to show if we have both of them up to n, we get 1n plus 1. And we had one proposition. So remember what we want to show. We want to show if we've got a bunch of definable sets, finitely many, then there's a cell decomposition of the ambient space, which is compatible with each of them. And we stated this proposition here, which says if you have 2 cell decompositions, then there's a common refinement. So that was proved under the inductive assumptions. So by this proposition, we can assume that there's only one of these x's. So proof of 1n plus 1. So by this proposition 1 here, we can assume k, so the number of sets we've got is 1. And then we had this other proposition that told us, so we had a notion of a type of a 1 variable set, which was telling us for each, it gives us the boundary or the cardinality of the boundary and tells us for each of the possible intervals and points whether or not they're in the set. And then we had this proposition here saying if we have a family of 1 variable sets, then the set of possible types is finite. And then for each possible type, the set of parameters where we have that type is definable. So by this, and using cell decomposition in Rn, we can assume that the type is constant. So by proposition 2, and cell decomposition in Rn, so we're trying to prove cell decomposition in Rn plus 1, we get a cell decomposition d of R to the n, such that for each cell in the decomposition, there is an L and a type such that over each of the points in our cell, our set X has that type. So such that the fiber over this X is the given type for all X in the cell. So we fix one of these C's and the tau on the L. So then as we vary X in C, the cardinality of the boundary of the fiber is constant, it's L. And then, so we can define functions on C by saying on the first element of the boundary or the second element of the boundary and so on. So we get definable functions F1 up to FL defined on C such that F1 is less than F2 is less than and so on up to FL, and such that each possible interval over C is either contained in X or disjoint from X. Where F0 is minus infinity, FL plus 1 is plus infinity. So this is for I is 0 to L. And the same is true of the graphs. And graph of fi's contained in X or disjoint from X. For I equal 1 up to L. Okay, now then, so now I've got a bunch of definable functions. So I can use, they're all defined on this cell C, which is in R to the N. So I can use the second part of the cell decomposition statement, this bit, to assume that all of those are continuous, or to partition C such that they're all continuous. So by 2n, we can partition C into finitely many cells. So that F is continuous on each cell. So I'm almost done. All I need to do now is apply 1n again to make sure. So at this point, we have a cell we have a decomposition into cells, but it's not a cell decomposition. They might not line up. So I apply 1n once more to get them to line up. Then apply 1n to get us over to decomposition. Of Rn compatible with all of the resulting cells from this first part. And then taking those graphs over those cells will give us the cell decomposition of R to the n plus 1. Okay, so that's the end of the proof of cell decomposition, assuming these extra things which I assumed. So for the full proof, you can see either the paper by Knight, Pila and Steinhorn or Lau's book. Okay, so then I was going to make a remark. This is nothing to do with cell decomposition, but this seemed, I didn't want to make it at the start of the, like in the middle of the proof. So in the questions on Wednesday, Mikhail asked about parameters. So in the definition of O-minimality, we demanded that sets definable with parameters have to be finite unions of points and intervals. Right? So remember that the definition of O-minimality requires sets, all definable sets with parameters to be finite unions of points and intervals. And you can make a definition where you only require that for sets definable without parameters. And Chris pointed out that that's genuinely weaker. So if we only assume this for sets definable without parameters, what we get is genuinely weaker. We don't get O-minimality in general. So there's a counterexample due to Alf Dulwich, Chris, and Charlie Steinhorn. So I can't remember the date of the paper. It was 2000 something. And it is, you take R less than V, where V is the Vitali set. So that's the points in the plane such that their difference is rational. So this has a name, it's called the Vitali relation. And then the only zero definable subsets are R in the empty set. And only zero definable subsets of R are R in the empty set. So the only empty set definable subsets of R are the empty set and R. So it would fit the definition of being empty set O-minimal because these are unions of point intervals. But as soon as you name a parameter for zero, you can define the rationals. But over zero, Q is definable. So it's not O-minimal. So thanks to Chris for pointing that out. Okay. So now I was going to go back to cell decomposition and point out a consequence for kind of connectedness. So in our setting where we have just a dense linear order, an interval might not be connected topologically. So note that an open interval in M sorry. Okay, I thought my pen wasn't going to work. I was a bit worried. Might not be connected. So for instance, e.g. Q, which is an interval in Q, is the disjoint union of the open sets minus infinity root 2, union root 2, infinity, where this is bad notation because these aren't intervals, but you can guess what I mean. So topologically, like our underlying set might not be connected, but it is connected with respect to definable sets, definable open sets. So definition, definable set is definably connected if you can't write it as the union of two disjoint definable open subsets of X. So if non-empty, so if X is not the union of two disjoint non-empty definable open subsets of X. So then you like intervals are definably connected, and in fact cells are. So you can prove that by induction. So e.g. cells are definably connected. And then using cell decomposition, you can show that definable sets have finite many definably connected components. So that's maximal definably connected subsets. And then that's uniform as well. So proposition, suppose that I have some subset of m to the m plus n is definable. And there is n such that if x is an m to the n, then the fiber has at most big N definably connected components. So the fiber over x has at most big N definably connected components. So in particular, you get the uniform finiteness that we assumed. And the consequence of that is that if I take another structure that's elementarily equivalent, so a structure in the same language as my M, I take some N, it's elementary equivalent to M, then N is also O-minimal. So in the stability world, when you have minimality, it's not true that it's preserved under elementary equivalence, and that's why you have strong minimality. But there's no notion of, well, you can make a notion of strongly O-minimal, but it's the same, and that's why we don't have it. That's why we don't talk about it. So this is very useful, and we'll use this later. So yeah, this says O-minimal implies strong, basically, but that's why you don't say strong minimal. Okay, so next I was going to talk about definable choice, curve selection, before we do dimension. And here, because I don't like examples like this, I'm going to just assume that we expand a field. Well, not that I don't like them, I don't want to think about them. Okay, so from now on, we assume that N is no longer just an expansion of a dense linear order without endpoints, and it's an expansion of an ordered field, and it's O-minimal. It's an O-minimal expansion of an ordered field. And you can check that that ordered field is then necessarily a real closed field. So this is overkill for this section, but I'm just going to assume it anyway. Okay, so what's definable choice is a very useful thing. So what does it say? So it's got two bits. If I have a definable family, I can definably pick elements of the fibers. So if X in M to the M plus N is definable, and pi's projection down to the first n coordinates then there's a definable map f from the projection to m to the n whose graph lies in X. So, such that graph of F is a subset of X. And then the second part says if we have a definable equivalence relation, on a definable set X, then E has a definable set of representatives. Okay, so let's prove these. So for the proof, we show that if x in m to the n is definable and non-empty, then we can definably pick an element of x, an element ex of x. So how do we do it? Well, we do it by induction. And so if n is 1 and x is non-empty, then what's x? It's a finite union of points and intervals. So either it has a least element, then we pick that. If it doesn't have a least element, it has a leftmost interval. And then let's see, if that leftmost interval is the whole thing, we can pick 0. If it's like minus infinity to some b, we can pick b minus 1, and so on. So I'll write that down. So if e of x, if x, let's, so do the case n equals 1. If x has a least element, let e of x be that. Otherwise, let a be the leftmost interval of x. And then you just do cases. E of x is 0 if a is minus infinity, b is plus infinity, b minus 1 if a is minus infinity, b is an element of m, a plus 1 if it's the other way around, a is in m, b is plus infinity, and the midpoint if they're both elements of m. And these things now make sense, right? Because we've got some extra structure on our set. So we have a plus and a division by 2. Okay, and that's the n equals 1 case, so then you can finish inductively to get this e of x in general. And then how do you prove 1? So for 1, definably without parameters, if it is definable without parameters, yes. So then for 1, you put f of little x to be this element of the fiber. And then for 2, that's for x in the projection, so that the fiber is not empty. And then for 2, if I take E of A, where A is an equivalence class of E, that gives me a definable set of representatives. Okay, and then using this choice, we can prove a useful result called curve selection. So, later when I move the page up. So this is curve selection. So suppose x is definable, and I have a point in the frontier of x. So that's the topological closure of x minus x. Then I can find a continuous definable function that's injective from some small interval 0 epsilon to x, whose limit as I go to 0 is a. So then there is a definable, there is a continuous definable injective gamma from 0 epsilon to x, some epsilon, such that the limit of gamma of t as I go to 0 is my point A. So you've got, I don't know, some surface, say, and you've got a point in the frontier, and this gives you a little curve that goes up to that point. So this is the image of gamma here. Okay, so this is easy using what we just proved. So let's let norm of x be the max norm. And then since my point is in the frontier, if I take the norms of a minus x as x varies over my set, so that's a definable set, and it contains arbitrarily small positive elements. And it's definable, so it contains some interval 0. And then for t in that interval, the set of x such that the norm of a minus x is t, it's going to be non-empty. So if t is in 0 epsilon, then the set x in x such that a minus x equals t is non-empty. So by definable choice, we can get a definable function, a definable map that takes t to some x, such that a minus x is t. By definable choice, we get a definable gamma such that a minus gamma of t has norm t for t in 0 epsilon. So then clearly gamma is injective. And it has limit a. Sorry, lim gamma of t equals a. And then by applying the monotonicity theorem, I can perhaps reduce epsilon and assume that gamma is continuous. Okay, and that's the proof of curve selection. So next we're going to do dimension. So for dimension, first of all, we're going to do dimension theory via cell decomposition, and then we'll do it via like generic points. We'll show that at the side. So I continue with my assumption that I have a field. Though we don't actually need this for this section, but it's convenient. And then the definition of dimension, well, I take an x. So suppose x is a subset of n to the n, it's definable and non-empty. Then I put dim x to be the maximum of the I1 plus to IN such that x contains an I1 up to IN cell. And then I'll put the dimension of the empty set to be minus infinity. So this is like an ad hoc definition of dimension, but we're going to prove that it has lots of nice properties, so it's the right definition. I mean, it agrees with kind of any reasonable definition of dimension. So to do that, we need a lemma. So this says if I have a subset of m to the n and it has non-empty interior, and I have a definable injective map to m to the n, then the image of x under f contains an open cell. So I'll prove this lemma, and then we can prove kind of things like the dimension is invariant and the definable projections. So let's prove the lemma. So the proof will be by induction on n. Okay, so if n is 1, then x is a subset of n with non-empty interior, so it's infinite. F is injective, so f of x is infinite, and it's definable, so it contains an open interval. Then, since x is infinite, f of x is also infinite by the injectivity and definable. So f of x contains an open interval, which is an open cell in it. Okay, so let's suppose n is bigger than 1. So by cell decomposition, we can assume that x is an open cell. And that f is continuous. So then I can cell decompose the image. So apply cell decomposition. to f of x. So f is C1 union up to CK for some cells. In m to the n. So I'm done if one of these is open, so suppose none of them are open. Okay, so then since X is the union of the pre-images, and X is open, one of these pre-images contains an open cell. C contained in m to the n. So let's say C is contained in F inverse of C1. Okay, so then if I look at the restriction of F to C, let's send C to C1, that's continuous, definable, and injective. Okay, now remember that an I1 up to IN cell is definably homeomorphic to an open cell in M to the I1 plus up to plus IN. And in expansions of fields, open cells are definably homeomorphic to the ambient space. So since we expand the field, open cells A in M to the L or M to the M are definably homeomorphic to M to the M. So C is definably homeomorphic to M to the N, and C1 is definably homeomorphic to M to the L for some L less than N. So that one's definably homeomorphic to M to the N, and C1 is definitely homeomorphic to M to the L, some L less than M. And then composing with this, we get a definable continuous injective G from M to the N to M to the L. And then I can define H from M to the L to M to the L by sending Y to H of 0Y, where that 0 is in M to the N minus L. So L is less than, that's an N. L is less than N. We have a definable injective map from M to the L to N to the L. So its image has interior by the inductive hypothesis. So H of M to the L has interior. So let's take a point in its interior. Let B be in the interior of h of n to the L. So then B is h of A for some A in m to the L. Now G is continuous. If I take, so if I take a x in where n to the n minus L not 0 is sufficiently small, then G of xa will be close to G of to h of A. So G of that should be a G. Sorry, be close to G of 0A. So it will be in the image of H. G of xa is in the image of H. So it's equal to H of something. So there's an A prime in M to the L such that H of A prime is G of xa. And then by the definition of H, that's equal to G of 0 A prime. But these are different, so G is not injective, and we assumed it was. This contradicts injectivity. G. So that means all the cells in our cell decomposition of the image of X, at least one of the cells in our cell decomposition of the image of X must be open. And so f of X contains an open cell. Okay, so next we have we're going to show the invariance of dimension under definable bijections. So let's state what we're going to prove. So 1, if I have X contained in Y and Y is contained in M to the N, then, and they're definable, then the dimension of X is less than or equal to the dimension of Y is less than or equal to N. 2, if X is in M to the M, Y in M to the N, definable, and I have a definable bijection, then they have the same dimension, X and Y. And 3, if I have X, Y in M to the N definable, then the dimension of the union is the maximum dimensions of 2. So let's see. I've got 5 minutes left. So I'll prove 3. Well, 1 is easy, right? There's nothing to do there. I'll prove 3 assuming 2, and then we'll prove 2 next time. So proof of 2 next time. Let's prove 3. So let's see, let's let D be the dimension of the union, and take an I1 up to IN cell C in the union where I1 up to In sum to D. So a cell witnessing the dimension of X union Y is D. Okay, so then I can let phi from C to N to the D be a definable bijection by what we said before. So M to the D is C's contained in the union, so it's the image of C intersect X together with C intersect Y. And this is open, so one of these two contains an open cell. And hence, one of phi of C intersect X, phi of C intersect Y contains an open cell D. So let's say D is contained in phi of C intersect X. Well, then phi inverse of D is contained in X. By part 2, which we'll prove next time, phi inverse of D has dimension D. Well, it's the dimension of D, which is D. So D, oops, so dim X is at least D, but D was the dimension of the union and X is contained in the union, so that's at least the dimension of X. Okay, so that's the proof of, so dim X equals D. So that's the proof of 3. And then next time we'll prove 2. I will prove some other kind of geometric things about dimension before we do some model theory. Okay, so I'll stop there.
Thank you, Gareth.
Thank you.